Yeah, hi everybody. It's nice to be here, and thank you, Mike, for the invitation. So I'm going to talk about Earth MRI, which many of you may be familiar with. I know USGS has participated in these workshops in recent years. It's my first time to Rolla, so it's cool to be here and to see some rocks on the way down from St. Louis yesterday evening. So Earth MRI is 6 years old this year. I've only been in this position about 2 years. I was a research geologist, geologic mapper, and led the Alaska Geology Group for the USGS prior to coming into this role. But Earth MRI started in 2019 with a goal to modernize the mapping of the nation. It was recognized and pointed out many times by various advocates that we just don't have good data for making sound, data-driven decisions, particularly in the mineral resources space across the country, certainly when you compare us to many developed nations and also many developing nations. And so we got new funding from Congress to the tune of about $10 million a year. It was initially envisioned as a 10-year program, but we've been baked into the USGS Mineral Resources Program budget, so we will endure, at least for the foreseeable future. And then the Energy Act of 2020 directed the USGS to focus specifically on critical mineral resources. And so Earth MRI went from a broadly geoscience data-driven mission to a critical minerals-focused mission, which of course also has overlaps with broader geoscience questions that are in the national interest. We also got a significant funding stimulus through the Infrastructure Investment and Jobs Act. So from 2022 through 2026, which is next year, we received $320 million, $64 million a year over 5 years, which for the USGS is a significant increase. So that increase both accelerated our data collection across the United States, and it also gave us the opportunity to expand our portfolio. And I'll talk about some of the outcomes of that later. We also have the ability to take in disaster supplemental funding, and so in 2023 we did receive $5 million in disaster supplemental funding to support data collection around hurricane resilience and recovery in Florida and Puerto Rico. And so the data collection that we did was completely in line with what Earth MRI was already doing. We simply took it and applied it to a different set of problems in cooperation with state and territorial partners. It's as I mentioned, it's no surprise that the data that we're going to talk about have direct mineral resource applications, but we also try to highlight the other applications these data have, particularly with energy resources. There's a lot of interest at the federal level on geothermal energy, and we know there are direct ties between geothermal and things like lithium out west. We have obvious connections to hazards, water resources, infrastructure, et cetera, and we obviously work in the service of the land management agencies within the federal government. We partner, Earth MRI is a partnering program, and some of our key partners are the state geological surveys. I see some folks from the Missouri survey out here, and we've been partnering with them since the start of Earth MRI. We partner with other federal agencies, NASA, DOE, et cetera. We partner with tribes where possible. We partner with industry, and we're always looking to expand these partnerships where we have mutual interest and mutual need for the types of data that we collect. So I'm going to talk just generally about the different data sets that we collect, show you some examples. This is just the tip of the iceberg, and I'll also acknowledge that this is way upstream from many of the concerns that may reside here in the room. But I think that the results from Earth MRI and the work we're doing for the value of the nation and for the industry and for the states like Missouri will hopefully trickle down and have benefits for everybody here. Earth MRI was really built around high-quality topographic mapping, LiDAR data, high-quality geologic mapping that's done by our state geological survey partners, and airborne geophysics, which allow us to map and model the geology across large regions of the United States, really to help with the sort of domestic resource assessments that the USGS is tasked with. Through the Infrastructure Investment and Jobs Act supplement, we were able to add hyperspectral remote sensing. We have a partnership with NASA over 4 years, where we're getting new high-altitude data collected over most of the arid western U.S. We're also doing district-scale studies, which are actually going to occur here in Missouri probably later this year. I'll talk about those more in a minute. The IIJA directed us to focus on mine waste. I know there's a lot of interest and discussion around mine waste and critical mineral potential in mine waste, and so we have some dedicated programs to inventory and characterize mine waste. We also support data preservation efforts by our state partners, recognizing that there's tons of relevant information that's buried in our archives, buried in our rock collections, and if we can bring that material to the surface, get some new data, and bring that data into public space, then we can all benefit from it. One of the challenges that we still have is that our data delivery mechanisms are highly decentralized, for lack of a better term. These are some of the places where we store the data. All the data that we generate and contribute to generating is in the public space. So not only is this data being generated, but it's being made public for all of us and all our whole stakeholder communities to use. So we have LiDAR data served through the national map, for example, airborne geophysical data served through USGS Science Base, geologic maps served through the National Geologic Map Database, in addition to state geological surveys, which are the authoritative sources for the geologic maps that they produce. National Geochemical Database, Geochronology Database, et cetera, et cetera, et cetera. We're working to consolidate these, but data delivery is not our specialty. And as we were making progress, some things changed in the federal workforce, so we're trying to get back on track. But stay tuned there. There's more to come. But the data are there if you have the patience and computer skills to find them. Or just ask me. We do have an acquisitions viewer, which is, I think, a valuable resource for those who are interested in Earth MRI. We update this acquisition viewer quarterly, and it goes back to the initiation of the project. It shows what we're doing, where we're doing it. It describes who's doing it, why we're doing it. So it provides quite a bit of metadata for the work that we're doing, and where projects have been completed, you can actually tunnel through to the data in an ideal scenario. I won't test that on the fly. It does also talk about the critical commodities. Of course, we try to link this to the critical mineral space. So if you're interested, for example, in where we're doing work that might relate to cobalt, rare earth elements, whichever commodity you have an interest in, you can actually go in and search and see where those projects are, and then you can get in touch with those doing the work to see, what they're doing, whether you might have some interest in it or value from it. We're always trying to build this up based on user feedback. So if you go in and look through the acquisitions viewer and find something that you think could be done better or could address an interest or concern of yours, please do reach out. We're always available to receive feedback from the community, and we're trying to grow the community of people who are noticing this and using it. So I'll start talking a little bit about the data that we're collecting, and I want to start by talking about the mineral systems framework that helps us prioritize the data. When the new funding came in, the administration said, develop a plan. The executive order said USGS will submit a plan. And the first part of the plan was to figure out where in the heck we would actually do the work, recognizing that we don't have the resources to work everywhere on all the problems all the time. We put together a team of experts that involved the USGS and our state partners to map out the mineral systems of the nation. And the mineral systems framework has been around for the last couple of decades. We're working with international partners, namely Canada and Australia, to develop a global mineral system framework. But this mineral system framework basically takes all of the possible mineral resources that can occur in any prospective geologic environment. We map those geologic environments on the landscape, and so then we can match those with, say, what are the commodities of greatest need, what are the commodities of greatest interest, what are the state's priorities, what are our research strengths, what are our research priorities. And so we can do work focused on these various systems depending on the commodities that might exist in them. We like the system, too, because it kind of future-proofs us against potential changes in the critical minerals list. There's going to be a new critical minerals list coming out from the USGS this year. If the list changes, which it may well do, we can just plug those new critical commodities into this framework and say, oh, now commodity X is on the list. Where should we go and invest in understanding more about the mineral systems that host that commodity? So we think this is an adaptable framework. It's scalable, it's flexible, and it's going to continue to change. Ideally, as we learn more, this map changes. Hopefully it doesn't change by too much. Hopefully it grows. It will probably shrink in some areas. But nevertheless, this is our framework, and this is where we're operating. And this is published in a couple different places in USGS reports. So talk a little bit more about the data portfolio. This is a map that we're really proud of. When we started investing in LiDAR in 2019, our LiDAR investments flow through the USGS 3D elevation program. And phase one of the 3D elevation program is to complete the LiDAR coverage for the entire nation, IFSAR in Alaska. I always like that asterisk. We don't get LiDAR in Alaska as a baseline because we're too big. So we have 5-meter IFSAR. But if you look at the map on, let's see, it'd be on the lower left, that shows the state of LiDAR coverage for the nation before Earth MRI started. And you can see the map on the right that shows all of the LiDAR acquisitions completed or in progress. And I don't know if you can see the purple hatching, but those are the Earth MRI contributions. We've helped fill in the West, which is really helpful because that's where a lot of mineral potential lies. But nevertheless, 3DEP is now, I think the most recent number was something like 98.7% complete for the nation. And so that's a major accomplishment that the USGS is proud of. And now, USGS and other partners are trying to figure out what's next. There's 3-depth next-gen LiDAR, for example. We've also brought LiDAR into Alaska, particularly focused on mapping mine waste sites. We recognize that 5-meter LiDAR can recognize some features on the ground, but it just can't resolve things at a level of detail that we need for delineating surface features like tailings, for example. So we're bringing investments into Alaska for LiDAR with hope of covering the state, but it seems unlikely to do that in campaign style at this point. I'll just show you an example. Oh my gosh, it gets probably washed out on the screen. Just an example of why LiDAR is relevant. This is an example from near Marquette, Marquette, Michigan, up on the UP. You can actually see in the LiDAR, you can see an active iron mine. You can map out the tailings of that iron mine. But most importantly to me as a geologic mapper, you can strip off the trees and see where in the world the rocks are if you want to go out and map them. So if you're a geologic mapper and you're not working in the mountainous west or the mountainous regions of Alaska and you got to walk through the trees or the swamps to find the rocks, the LiDAR helps you find the rocks to make a more informed map. So that's why the LiDAR has been incredibly important for us and for our mapping partners. Geophysical data really underwrites most of our program. It's a strength that the USGS has had for quite a long time. And just taking one particular type of data, airborne magnetics, I'll show you an example of what airborne mag looks like here in a moment. But again, in the lower left is our pre-Earth MRI availability of what we considered reasonable quality airborne magnetics for geologic mapping and modeling. And the coverage was pitiful. It was really dreadful. We've made major strides in new high-quality systematic coverage in all regions of the nation. The map you see there on the right is our current footprint of the U.S. for high-quality airborne magnetic data. And the increases have been staggering. In the early years of Earth MRI, we added about the size of Texas. Through the supplemental funding, we're adding about the size of Montana in new coverage every year. And we're on pace to do the same thing here in 25. So we're excited by these data. The acquisition, the contracting and acquisition data of these data and the acceleration of it has almost broken our contractors, but we're actually building capacity. We're bringing new contractors into the country. We're actually increasing USGS contractor capacity through these sustained investments. And so there's a lot of value added, not just in the science, but in the contracting space that'll obviously, hopefully benefit the minerals industry and other industries as well that rely on these data. This is a map that just shows the coverage on top of our mineral systems map. And the thing that I really want to highlight here that I didn't fully appreciate when Earth MRI got started, when Earth MRI started, I was sitting in Alaska, and I was interested in Alaska geology, and I would argue that among the United States, our data gaps are most significant in Alaska because it's a big place. There's a lot of cover, despite the mountainous parts of Alaska. There's a lot of cover, there's a lot of water on the surface, and so I would also argue that it's a mineral resources frontier. There are major discoveries to be made and potentially to be mined in Alaska. We just don't know where they are, and if we know where they are, we just don't know enough about them to say what the resource is, what the context is, et cetera. But the important thing about this map is it shows that there is mineral potential across the entire United States. And you've already heard about mineral potential in mining here historically and actively in Missouri. And so we've invested in the East Coast, the Mid-Continent, and the West, and Alaska sort of intentionally to make sure that whatever mineral questions exist in a certain part of the U.S., we have the ability to collect new data that helps stakeholders, land managers, communities, et cetera, make informed decisions about those resources, and hopefully help industry explore for them as well. If you just want to look at the sort of improvement in data quality, it's staggering. There are plenty of examples to choose from. This is just one that's fairly new and pretty compelling. This is a new airborne mag data set from the Medicine Bow Mountains in southern Wyoming, just west of Laramie. If you look at the lower left, that's sort of the existing quality of data before Earth MRI. If you look in the upper center, that's the new data. And again, this is a rugged mountainous region, so there is good exposure, but it's hard country to work in. And then around the mountainous regions, there are basins that cover up the rocks that have the most potential. It's also heavily forested in certain areas. And so these data allow us to see patterns that simply weren't available to us before. The radiometric data, when we collect magnetic data, we also collect radiometric data, which measures natural gamma ray signatures emitted from rock, sediment, soil at the surface. So we can actually map superficial features using the radiometric data. We partner with the Wyoming Geological Survey in this case to do geologic mapping, to collect new geochemistry. We partner with industry. The blow up on the lower part is the Lake Owen complex, which has known platinum group element potential there in southern Wyoming. And so we've partnered with industry to enhance the data in this particular area to benefit them. And so to us, it's win, 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 and the quality of the data is just transforming our ability to map and model our geologic framework and the mineral resources that are hosted within that geology. So this is just one of many examples, and I'd be happy to show you some other examples offline. This is an example from Alaska. As I mentioned, the IIJA allowed us to expand our data collection portfolio. We added airborne electromagnetic data, and that's something that we hadn't done before under the regular Earth MRI program. Electromagnetic data is sensitive to the conductivity structure of the Earth, and there are some mineral systems that are particularly suited for conductivity measurements, namely lithium and graphite. And in western Alaska, there is the largest flake graphite resource in the United States called Graphite Creek, and so we actually flew a big airborne survey over the mountainous regions of the Seward Peninsula in Alaska to try to see where other graphite potential could be beyond Graphite Creek. And I won't go through the details, but you'll see the map on the top here shows the conductivity or the resistivity at a slice. I think this is 30 meters below the ground. It also shows the mag intensity, and then in cross-section you can see the Graphite Creek deposit there on the left with a star, and you can see values throughout the ranges that correspond to values that are underlying Graphite Creek to show that there's significant graphite potential here that's simply unrecognized at the moment. And so we're trying to get new geologic mapping out there. I'm sure the company that owns Graphite Creek is looking to do more exploration, and you'll see this beautiful core there with beautiful flake graphite and garnet there from western Alaska. We're funding geologic mapping by state survey partners, as I said. This year alone, we're pushing out this number is actually up to 26 now, 26 state geological survey mapping projects this year. We're actually going through that process now. It's a little bit delayed for various reasons that I won't go into. But we're pushing out roughly $10 million to $12 million to the state, directly to states each year now for geologic mapping. To date, we've funded 105 different projects, 31 geochemical mapping projects. We're working with 39 different states, 1 territory, and we seem to be adding new state partners every year. I don't know that we'll get to 50 states, but we're certainly trying. And some of that money is funded from the disaster supplemental, but most of it is core to Earth MRI. Of course, these numbers are inflated by the supplemental funding. We have 1 more year of supplemental funding, and we're going to make as many investments as we can. Things will then go back to our baseline, and so the landscape for funding will change, but Earth MRI will endure, and these partnerships will continue, just with a slightly different sort of order of magnitude, back to the old days, perhaps. As I mentioned, one of the things that we added through the supplemental funding is also hyperspectral remote sensing. This is, again, a partnership with NASA over 4 years, $16 million, using their high-altitude E-2 aircraft. And so this thing flies up at like 85,000 feet. We're doing sorties over most of the western U.S. We've covered all of California, which is remarkable. I think we're on track to cover all of Nevada this year, although they've had some weather considerations that might limit the full scope of activities. But we're getting coverage across, I think, 10 different western states. We've covered the entire trace of the San Andreas Fault system. And so we're excited about these data. We're excited about the partnership with NASA. NASA's excited to be working in the critical minerals space here on Earth. So that's pretty cool. You can see there, you might not be able to see in black, but we actually, through the funding, we expect to get across Utah into western Colorado, western New Mexico, and we're working in parts of West Texas this year. So this is a technique that isn't suited for everywhere. In fact, people always say, why aren't you doing this in Alaska? Well, it turns out there's a lot of vegetation and a lot of water, and hyperspectral remote sensing doesn't really work as well if you don't have bare rock, bare soil. It works well if you do have those things, but Alaska is challenged in that regard. So that's why we're focusing our efforts in the West, but certainly with new technologies, we might be able to sense things better using more advanced sensors. So TBD on the regional mapping effort. But if you want to see what these data look like, we're basically mapping mineral reflectance, solar reflectance off of mineral surfaces at a scale of wavelengths that has multitudes. That's why it's called hyperspectral. It's multispectral remote sensing. But we can use these multispectral responses to map mineral compositions in great detail. And this technique is particularly well suited for mapping hydrothermal alteration, which is a way that you can vector to ore deposits, particularly in the western U.S. And so these are just some examples of these mineral maps that our team is looking to make in the western United States. The cool thing that this team does, our team is actually out doing field calibrations as the NASA aircraft flies over. We have teams on the ground measuring the spectral signature on the ground level so we can calibrate it up to the measurements. They're also looking at satellite-borne sensors. And then we're also doing what are called district scale studies. We recognize that hyperspectral sensing can be used to map things like mine tailings. And so we're flying more detailed footprints at lower altitudes using contractors over mine waste sites. We started in Florida with the phosphogypsum stacks there. We've worked in New Mexico and Arizona. We're going to be doing a survey here in Oklahoma over the old lead belt, Pea Ridge, and in Tar Creek there in northeastern Oklahoma here in the next couple of months. And so it'll be cool to see what these data look like over these different areas. In the west, it's cool. They've actually been able to calibrate the ground and low altitude up to the E2 because they actually scheduled an overflight for the same day. And so we're getting these multi-scale calibrations and sort of, I think it's going to revolutionize the way these guys can work with these data. So more to come there. I mentioned mine waste. We are being, as I said, we were directed by Congress to focus on mine waste, and so we developed a few different initiatives. The first is USMIN. It's a mineral deposit database, but what USMIN has been doing is cataloging all mine features from topographic maps in the United States. One might think this has been done already, but it hadn't. One might think that AI/ML can do that. It can't. And so this is a very labor-intensive process. But this map, what this map shows is that mining is all over the place, historically, actively. You can talk about the differences in the mine waste of these sites. Some might be quarries, borrow pits, prospects, et cetera. Some might be full-fledged hard rock open pit mines. But nevertheless, this is a national there's a national footprint here. And so what we're doing now is diving into this footprint and figuring out where the actual waste piles of interest are. Where are things that are big enough to have some potential value? Where should we go actually characterize those things to see if they have critical minerals in them? And so this has led to a program that we now offer annually where our state partners can get funding to help with this inventory. And then they can also get funding to go out and sample these mine waste materials to characterize them for potential critical mineral resources. And I know the Missouri State Survey has been a beneficiary and is working with us on that. The Oklahoma Survey next door is, well, I think Illinois is as well. So all three states sort of in this area are working on this effort as we speak. So what's the point? Well, one of the things that we need to do is Congress told us to assess the critical mineral potential of the nation in 10 years from 2020. So we kind of have a 2030 deadline. And so we're turning all these data into assessments, national assessments or prospectivity maps of critical mineral resources. You need good data to make decisions. You need good data to make strong assessments. And so we're trying to build these data into integrated and scalable and adaptable assessment tools that can really tell the story of the data. And this is just an example from Alaska because we happen to have more sort of self-contained relevant data sets. The state of our data in the lower 48 is quite a bit different for various reasons. The other thing that we want to do is try to get from what I'd say research to resource potential. How can we actually use these to help others tell a story about the resources that might be in the ground? So this is an example from here in Missouri, Pea Ridge. And before Earth MRI started, there was actually mineral resource program investment in new airborne geophysical data over Pea Ridge in particular. And that spurred quite a bit of research that happened, I guess it's been about a decade now. But one of the things that they did was actually create a better understanding of the I would say the system underneath Pea Ridge. I don't know if this animation's not going to work here from this computer, but nevertheless, if you take these data that were processed and worked on perhaps a decade ago, and then you start to build on top of them with new Earth MRI data. We actually just flew a whole new survey over Missouri that included Pea Ridge. We're starting to get a better understanding of the three-dimensional structures of these mineral deposits. We can actually map the mine waste on the ground using the radiometric data, using the magnetic data, and hopefully folks can do the derivative work on this to decide, what the resource is. What is the rare earth element potential of this particular deposit? What is the rare earth element potential of the mine tailings that sit on site? There's a lot to be gained from these data, but we need good data to do the work. This is an example of what the thorium data look like. So I mentioned the radiometrics. This is a thorium map there on the left. This is on the right. You can actually see the outlines of the tailings there at the Pea Ridge site. We can actually map the tailings using the thorium. We can look at the thorium concentrations of the tailings and think about the rare earth associations. And then if you look at the little inset on the right, this is where the Missouri survey has done some sampling for mine waste characterization. So then we'll also characterize the physical materials, look at the mineralogy, look at the critical element concentrations, and characterize the waste there at that site. So it was a long-winded overview of Earth MRI. But the message that I want to leave you with is that we hope that these data will help transform our understanding of critical mineral resource potential here in the United States. It's certainly bolstering a whole array of research opportunities, both within the USGS, but within the private sector, with academia, and so on. We're going to continue to grow to the extent that we can. Of course, we're working on a short timeline with our supplemental funding, but nevertheless, love to hear from others who have thoughts on what we could do different, what we can do better, or how we can do work that is a direct benefit to you. So thanks for the time and interest.